So now let's talk about sarcomere length and orientation. Okay, so we've talked about some modulators of force and power within the sarcomere, and therefore within the muscle. So, and with most things in the body, as we'll talk about, and we have talked about, you'll find that there's kind of an optimal balance between things. Okay, the sarcomere is no different. So, within a sarcomere, if we look at this graph here, on this axis right here, the y-axis. Okay, on the y-axis here, we have the measurement is relative tension, but really that's ability to produce force. Okay, so if we look at this y-axis is force. Okay, so production of force, and then we have resting length, or percent of resting length. Alright, so at 100% here, this is normal resting length. Okay, so as we read this, of course having a higher number means that the sarcomere is able to produce more force at that giving percentage relative to its normal resting length. Alright, and what we find is that a sarcomere that's anywhere between about 80% here and about 120%, so give or take 20% of its normal resting length, that's your optimal range for producing force. Okay, so if we go above resting length, we see a pretty rapid decline in the ability to produce force. Likewise, if we go below this plus or minus 20%, we see an even steeper decline. Okay, so let's talk about that a little bit and see kind of what's going on with that. And it's pretty self-evident as we go along. So, if we look at this, here we have our myosin, okay, and then actin, of course. Okay, so we have our actin. Alright, so actin, myosin, these are cross bridges. Okay, so within an optimal orientation, that, resting plus or minus 20%, what you have is the ability for these cross bridges here to match up and align with the actin thin filament more optimally. Okay, more cross bridges are able to attach to more of the actin, and as we've said a number of times, force production of a sarcomere of a fiber is little more than the number of cross bridges attached at any given moment. So if I can attach more due to just the horizontal orientation of that actin and myosin, well, I'll produce more force. Okay, it's pretty simple, right? So if we go too far, right, going back to this, erase this, this area right here above, okay, or too far, right? It's above 120%. Once we start pulling too much, what you see is this orientation of cross bridge and myosin is not really able to grab onto the actin too well. So if you stretch a muscle too much, more than optimal length, then the actin and myosin aren't able to really interact in the way they would like to, and therefore you have less cross bridges attached, and as a consequence of that, you produce less force. Okay, the opposite is true as well. So if you're too close here, say you're sub that 80-ish%, which you saw was a lower range, say, of optimal, then what happens is the actin filaments are actually too close to each other, and they can actually kink and kind of overlap, and that doesn't help the myosin either. These cross bridges, they want this nice spread out orientation, right? They can grab onto the actin still has space to move. Okay, this is very neat, and you can see here we're starting to have overlap, and that's just going to reduce this sarcomere's ability to produce force. Okay, it's just that orientation is messing with those cross bridges being able to interact with their actin counterpart. So that's the horizontal. Now let's talk about the vertical. Okay, so this is a 3D structure. It's got dimension to it. So lattice spacing. Lattice spacing is this space between the actin and the myosin. Okay, this space right here. Okay, and typically this lattice spacing isn't perturbed too much, but there are instances such as dehydration to a great extent. So if you're very dehydrated, dehydration means that your cells don't have as much fluid inside of them as they would like. Okay, they're less than optimally hydrated. Okay, and if you have less fluid, then that means that everything inside of that cell kind of shrivels up a little bit. It becomes a little closer together. And as a consequence, you would see a reduction in lattice spacing. Okay, so if you have less lattice spacing, then the myosin cross bridges, once again, are not able to optimally grab onto the actin filaments. They'll still be able to, but it won't be as good as it could have been if it were properly hydrated and that lattice space were at its optimal. Okay, so it's like I said, this is going to be a recurring theme within physiology. There's always optimal ranges for things. Okay, so we just looked at the horizontal and now the vertical components of the sarcomere, and this, of course, the inability to grab onto actin in either one of those two instances will seriously reduce one's ability to produce power. Okay, which is really what we get out of the force that's produced by the cross bridges. Alright, so now let's talk a little bit about muscular performance development. Okay, so this is going to be a very short chapter compared to what it could be, and that's deliberate because in other courses, as you progress past exercise physiology, we're going to spend more time on this, and we're going to do it justice, so to speak. But it's worth touching on just to give you some of the foundational elements. So first off, before we get too deep into the physiology of it, I want to get past one of maybe the most important part of muscular performance, or physical performance. Okay. And I would say that is biomechanics and anthropomorphics. At least when we speak about producing large amounts of power. Okay. If we're talking about endurance, then we can make the argument, rightly so, that one's bioenergetics or metabolism is playing maybe a bigger part. But if I'm a power lifter, a gymnast, somebody any number of athletes who has to jump high, the number one thing that's going to contribute to that will be just the general anthropomorphics of my body. And by anthropomorphics, we're speaking of body segmentation. Here, this would be an anthropomorphic measurement. How long's the forearm, that sort of thing. Tendon attachment point, all that. Okay, that stuff is extremely important because some people just have a better advantage at sports. Okay. I put over here this, lanky versus stubby. It's very scientific, I know, but yeah, to a certain extent, some people have long arms and some people have shorter arms, and people who have shorter limbs are able to produce more force and produce better results in some sports. Okay, in some endeavors. Okay, so if any of you are out there, and probably most of you have at some point in your life performed a bench press or a push-up, I would wager that you're going to fall into two categories, give or take. One, you have long arms and long legs, and you have a hard time doing a lot of push-ups, and you're also probably going to be, maybe you don't like the bench press too much. Okay, it might be it's just not your thing. And here's the other category: people who are maybe shorter or just have shorter limbs. Okay, your arms aren't as long, and you can do push-ups all day, and your bench press is phenomenal. You're the envy of the gym. Okay, Now, to a certain extent, muscle has something to do with it, but at the same time, if you have shorter limbs, and I'm talking about a bench press, okay, this is about where the weight would be in my hand here. All I have to do is touch the chest, right? So this point to here is not nearly as long as this point to here, right? So the range of motion is shorter, first off. And also, if you have longer limbs, looking here at this arm we got here, your fulcrum, your lever is going to be longer. Okay, so as we know from just basic physics and honestly everyday life, if you have a weight at the end of a stick, it doesn't matter how much the weight is. It more is important how long the stick is, right? How long the lever is. Because if I put a 5 pound weight, see right here, but I have a 10-foot long pole that I have to lift that 5 pound weight up with, and I got to lift from right here, it's actually really hard. That's exceptionally difficult. Okay, but otherwise, if I have the same kind of thing, but instead I have a 1 foot long pole and put a 5 pounder over here, well, it's really easy. I can do it all day, right? So, levers and fulcrums and all that sort of stuff play a really big part in how well you're able to do certain sports, okay, and lifts and that sort of thing. So, we're not going to talk about a whole lot. It's really not this field. We take biomechanics as a separate course, so we can cover that. I'll cover it later in, like I say, some more advanced courses. But this is physiology. Okay, it's worth just saying. And I do like to take this time to address another thing which comes up from time to time, and it's really important. Okay, so I want to talk about youth sports, youth lifting. Okay, so probably at some point in your life, you've heard somebody say that you shouldn't lift weights until at least puberty, if not in your 20s. The fear being that if you lift weights, it will, wait for it, you can probably think of what I'm about to say next, stunt your growth. Okay, so let's talk about that, because that's a commonly held belief that is just really hard to get out of people because they've been told it for their whole life. So, does lifting weights stunt your growth? Short answer is no. Okay. There is a potential that if somebody were to become injured, if they somehow lifted incorrectly and damaged their bone at about the epiphyseal plate or lower than the epiphyseal plate, which is the growth plate as you're developing, and if you crack off or if you break that growth plate off, then the bone will stop growing. Okay. So maybe, sure, okay, if you have somebody doing exceptionally heavy weight and they're not trained to do it well, and they get injured, we could say yes, you might have a stunting of growth because you're damaging the bone that's actually going to cause growth. Barring that, there's no evidence that lifting weights or performing physical activity or certain sports will make you not grow as tall. Okay? And the root of this misconception really comes from people's perceptions of certain sports. Okay, and they see people who do certain sports and they go, let's talk first off about gymnasts. As we saw at the Olympics recently, Simone Biles. She's I believe 4'8" or so athlete, short limbs, exceptionally powerful, and she's phenomenal at gymnastics. Some people would look at that and say, oh, well, because she's done gymnastics, she's shorter than other people. And the same will also be true for people. They'll look at power lifters and Olympic lifters and look at them and they'll say, well, really good power lifters are often short. that must mean that because they were lifting weights, the weights, the weight that they were under somehow compressed their bones or their spine or made them stop growing. Now I want you to take a second here and really think about that argument, okay? Because that argument is exactly the same as if I were to say something like playing basketball makes you taller, okay? And you'll if I say that, it immediately sounds absurd. Um, you can point that out, right? If you're taller, you just happen to be better at basketball because you're closer to the hoop. Pretty simple. Well, the same thing can be said for gymnastics and powerlifting. If you're shorter in powerlifting, you get to take advantage of having a shorter range of motion, okay? And you have shorter levers. So you're able to move more weight, okay? It doesn't mean that your muscles are actually stronger. What it means is that the muscles that you do have an easier time moving weight because the lever action is better and you don't even have as far to move it. So you have a great advantage at doing powerlifting. Okay? Also, powerlifting is a strength to weight activity. If you're shorter, you don't weigh as much. So think about it. You don't weigh as much, which means you can go into a lighter weight class. Your levers are shorter, which means you get more force per muscle fiber, essentially. And you don't have to move the weight as far because your limbs are shorter. So, and there's some exceptions to this. Some people you could say, well, having long arms is actually advantageous for the deadlift. But by and large, many successful powerlifters are shorter. In gymnastics, you get a lot of the same things. Also, having shorter limbs helps you with your center rotation. So when you're doing flips and turns and things in the air, you're able to execute them more crisply than if you had longer limbs. So you have advantages. So it's not to say that doing these things will make you shorter. And by extension, lifting weights as a young person does not make you shorter. And every professional organization out there that's covered this would back this up. Okay, there's guidelines on this. It's simply that you have an advantage at a sport, therefore you're more likely to be competitive at it. Okay, off tangent. Let's move on. So, with development of performance, let's talk about the time course of things to a certain extent. Okay, so some of you have maybe gone through a period of detraining or have been sedentary for a few weeks or maybe years, or trained somebody who has been sedentary for a while, and when they just start lifting weights, they notice rapid growth. Not growth so much, but growth in strength. They're able to move weights where the first day they have a real hard time with it, and within a couple days, a week or two, they're going up in weight. And then a couple weeks later, they're going up in weight again. And they feel phenomenal. You feel phenomenal because you're just having leaps and bounds kind of growth. Okay, and that's pretty common for the first 8 weeks or so, the first 2 months ish. You can see as much as a 10 to 20% increase in strength. It's very typical, right? Now, the problem with that is you don't actually see significant muscle growth, typically, until about 16 workouts on that specific muscle group. So think about this. Most people do 2 rotations of full body per week. We have 16 workouts. That gives us 8 weeks. Okay, so about 2 months in, that's when you're starting to see growth. Okay, so if you're not seeing significant growth within the first week when you're going up in weights, or the second week when you're going up in weights, we have to then say that something else must be responsible for this. Something else other than, say, just gaining that raw, increase in muscle fiber. Something else is happening there, and what that is that's neural factors. Okay, so as you move this thing real quick here. Oop, there we go. All right. So as you start to gain, as you start to lift weights, if you look at here, training studies, mostly just a few months, what you're seeing is increase in strength. This blue line here is strength. Okay, strength is going up, but you're not really seeing much hypertrophy until late into a few months into training. Okay, so to increase strength, what you're having is an increase in neural drive. Okay, so there are neural factors. Your nervous system is actually becoming more coordinated, and it's adapting to lifting weights, which is allowing you to have a greater strength that you're observing. Okay, and I want you to think of strength as being an interplay between the muscle, the tissue, okay, that's actually doing the movement, and then the neurology, which is controlling the muscle. Okay, so the major neural factors which change within the first few weeks and months of lifting, or really doing any physical activity, but lifting's we're talking about muscle. So anyway, the major things here are removal of inhibition, increasing coordination and neural drive, reducing or non-activation of antagonists, and reduced bilateral deficit. Okay, so let's talk about those individually. All right, so increasing neural drive. All right, so you can very easily state that performing any motor task, any movement of your body, is little more than firing the right muscle fiber at the right time or in sequence. Okay, and it sounds exceptionally simple, and it is. It's a very simplistic way to look at it. Realistically, a lot of motor patterns are very intricate, and they take a long time to develop. Um, the correct optimal way to do them. Okay, so the more repetition that you do of anything, you can increase the sequencing or the coordination of firing the right motor units at the right time. Okay, um, and that's not only within an individual muscle, but also its agonists. Okay, agonists are muscles which help move a joint about a range of motion. Okay, so essentially through training, through lifting weights in this instance, we'll say, what you get is the ability to recruit less motor units, because initially when you start to do an activity that you haven't done before, your body will have your nervous system in the motor cortex will activate more motor units that are than are actually required to do the task. Because essentially, it doesn't know how much it needs. Okay, your body doesn't know how much it needs to do the task, so you'll have a tendency to overactivate. Okay, um, and you'll get varying results from this. Sometimes it just kind of looks a little bit, for lack of a term, spastic. Okay, it's uncoordinated. If you ever watch a 2-year-old run, okay, um, it's not nearly as refined as a 20-year-old. Okay, and quite simply, it's just that the neural patterns, the motor patterns of that 2-year-old have not had as long to develop. Okay, so with time you get more coordination. Now, it is worth saying within this that you will still require activation of the same amount of motor units to perform a maximal task. Okay, because intrinsic with that term maximal is using all of your capacities. So, no matter how much you train, if you're doing a maximal effort, you will use all of your musculature that you're able to recruit. Okay, so removal of inhibition. Okay. Now, and I've talked about before the fact that when you do lift weights or say perform a 1 repetition max in the gym, you're not really using all that you're capable of doing. You're performing what's called a maximal volitional contraction, okay, an MVC. Okay, that's the maximum that you are capable of doing. But the body always inhibits to a certain extent. It doesn't really let you do a full contraction because it's a bit of a defensive mechanism. Okay, one of those mechanisms there that contribute to that is the Golgi tendon organ reflex. Okay, so and we talked about this before, but when the GTO is stimulated, you get a couple things happening. Agonists are inhibited. So in the case of say doing a bicep curl, okay, the bicep is the agonist because it is the thing that's actually mostly it's the major mover there. It's the main mover trying to move my forearm up, which has a weight in the hand, of course, and I'm going to try to bring it up toward my shoulder. Okay. So you'll have inhibition of the agonist, and also you'll have facilitation and or excitation of antagonists. Okay, so that same example, if I was doing a biceps curl, my antagonist would be the tricep, and if the Golgi tendon organ reflex is stimulated, once again through the sensation of exceptional loading on the tendon, on the muscle tendon unit, then that Golgi tendon organ will react by causing inhibition. Okay, so an untrained person, this is a very active reflex. Okay, with training, this reflex is reduced. Okay, so the Golgi tendon organ doesn't fire quite as much, although the force is there. Your body, to a certain extent, learns that the force that you're putting on your muscles is not a danger to it, and therefore this reflex is somewhat quieted. Okay, so another mechanism which changes with training is simply that you don't contract as much musculature. Okay, this kind of goes with coordination, but let's be a little more specific. Okay, as I said before, when you're performing a new motor task that you're not well acquainted with, your motor cortex often doesn't know specifically which motor units to activate. Okay, and that's going to lead to what you would perceive as uncoordinated movement. All right, and one of those things is the activation of your antagonist muscles. Okay, so simply put, if we are talking about a curl, okay, that same kind of biceps curl, all right, if I have, I'm going to draw a little, okay, arm here. This is a shoulder right here, all right, this is a shoulder, okay. We got our humerus, got an elbow, and there's my forearm, and here's my hand. Okay, I've got a weight here, okay, so this is my load, okay. Load, elbow. Alright, you get the picture. Alright, so here we have our bone structure, and now I got a tricep. It's such a phenomenal drawing here, but okay, I got a tricep, I got a bicep. Great. Okay, muscle belly is my bicep, my tricep, tendons. You know, this is real world accurate here. Okay, so if I have this going on, and I said, okay, I want to curl this weight up. Okay, my bicep is what I want to have activating, right? That's what I'm targeting, if you will. Okay, I'm going to try to activate my bicep, and then bicep is going to pull on its bone, you know, and it's going to pull it up toward the shoulder. Okay, that's what it's going to do. Now, if I'm untrained, what can happen is instead of just this bicep pulling up, let's say this bicep pulls with, I don't know, 15 pounds of force. Okay. Anyway, maybe I can, you know, the forces aren't all right with the leverages and the fulcrums and all that, but let's just say I have a total of 15 pounds of upward force. Okay, so that's my capacity. If my tricep activates here, even just a little bit, that makes a pretty significant impact on my ability to lift, right? Because if my tricep starts to pull, on the opposite side here, then what I'm getting is a downward pull, right? So let's say maybe that's only 5 pounds. Okay, but if this is 5 pounds and that's 15, the net is only 10, right? So as I become more coordinated, and maybe I stop having as much activation of that antagonist, then my net ability to produce force is 15. Does that make sense? Because this bicep hasn't really gotten stronger. All that's happened is I'm no longer activating my tricep. So now, the amount of force that I perceive I'm able to exert, or the amount of weight that I feel like I'm able to lift, has gone up. When in fact, I haven't really had any muscular change. I just got better at lifting the weight. Okay? So, it's important to understand that the amount of weight you're lifting has a lot to do with that the leverages and which muscles are contracting and how good you are at doing it. Okay, so just kind of be thinking about that as we go along. And the last thing I want to talk about is bilateral deficit. Don't need to spend too much time on it, but it is a phenomenon which is talked about sometimes. So I want you guys to be familiar with it. Okay, so bilateral deficit can be illustrated quite simply with a bench press. All right. So if I were to give you the example of just asking you to do this, if I asked you to go into a gym, and you'll know the answer to this if you lift weights, but if I would ask you to go into the gym and I said, okay, take a dumbbell, as in with this example right here, take a dumbbell and just with one arm, push it up as much as you can, as much as you can. Do like a 1 repetition max with this arm, okay? Get your right arm, and then do your left arm, and then add those things together, and then we're going to call that a combined, okay? All right. So if you did that, and then on the other instance, I asked you to do the same thing, say with rest, and put as much weight as you can on a barbell, and then use both hands. Which one do you think would result in a greater amount of weight being lifted? The sum of 2 arms individually doing work, or the combination of both arms working at the same time? Now, if you've ever lifted weights, unless you're some sort of an anomaly, the barbell is going to result in more weight being lifted nearly every time. Okay? The same can be said for doing single leg press, squats, leg extensions, and this kind of strange thing where if you do the same motion with each arm or leg, yet that not equaling to both of those things working at the same time, that's called bilateral deficit. Okay, and what it is the deficit of working bilateral versus unilateral. Okay, so with training, the bilateral deficit is reduced. Specifically, it's reduced more so in athletes who do a lot of single leg activities. Okay, so there's research that's been done in, say, like a cyclist versus like someone who rows crew. Okay, and when you row crew, you use both legs to press with your legs, and then also at the same time rowing. Whereas, of course, a cyclist is pushing. They're essentially doing a few thousand half one leg squats over and over again in short succession to turn the pedals. Okay, so each leg is working by itself every time it pushes a pedal. Right. And what they find is that the deficit between a cyclist and someone who rows crew is not quite as much. That is, a cyclist individual efforts, when combined, almost equal or do equal their double leg effort, whereas someone doing crew, their deficit is not reduced as much. So that's something you see with different athletics. All right, so muscular development. Okay, so here we're going to talk about how do we build muscles? What's actually happening when you're building muscle? Okay, so first off, let's talk about terminology a little bit. All right, hypertrophy, you've probably heard before. Hypertrophy is simply increasing the size of a muscle fiber. Okay, remember back to the anatomy of this, right? A muscle fiber, and within the muscle fiber, you're going to add myofibrils. Okay, so adding more myofibrils gives you more sarcomeres, gives you more actins and more myosins, and if you have more cross bridges able to attach to more actins, well then it's able to produce more force. Okay, so a bigger muscle fiber, a hypertrophied muscle fiber, produces more force because it has more cross bridges. Okay, that's pretty much all there is to it. All right. Now, hyperplasia is something you may or may not have heard of. Hyperplasia is increasing the number of muscle fibers in the whole muscle. Okay, and it's somewhat controversial, though generally accepted that it does occur. Okay. Now, both of these, hyperplasia and hypertrophy, are controlled by something called a satellite cell. All right, and we'll talk about that in a second. Okay, so in both instances, regardless if we're talking about hyperplasia or hypertrophy, we're getting more myofibrils acting in a unison on a tendon. Okay, because if I add more muscle fibers, it just means I'm adding new muscle fibers that have different innervation. But at the end of the day, that's more myofibrils, right? And if I hypertrophy an existing fiber, the nervous support to it hasn't really changed, but I just have more myofibrils added. So more actin, more myosin, more cross bridges gives you more power. Okay. Now, regardless of which of these processes is working, there does appear to be a post-lifting, post-workout period. We call it the open window. It's about 2 hours post-lifting where you'll have an increased protein synthesis. Okay, and you'll notice that increased period of protein synthesis corresponds pretty tightly with the nutritional recommendations, which are to take in extra protein right after you work out, and therefore you have more, we'll just say, bricks, if you will, to build the house out of, right? So if you have more protein in your system, you have a greater capacity to take it up, and if you have more protein going into cells which are looking to have protein synthesis occur, well, you have a greater period of rebuilding directly after working out. Now, intensity seems to be exceptionally important as it relates to training and muscular development. In general, training at higher intensities seems to cause a greater deal of hypertrophy than training at low intensities. Now, something that once again we'll talk about in much greater detail at a later time in a different class, training intensity is directly, or rather inversely related to training volume. That is to say, the total poundage I'll be able to lift at a lower intensity is much, much higher than the poundage I should be able to lift in a workout if I'm lifting at higher intensities. Intensity, by the way, in terms of resistance training, if you're not aware of the vocabulary, intensity speaks to percentage of maximal volitional contraction, or 1 repetition max. Okay, so if I'm working at 75%, that's 75% of my 1 repetition max. That would be the intensity of a lift. Okay, so let's talk about satellite cells a little bit. So satellite cells are themselves really they're undeveloped muscle fibers or muscle cells. Okay, when you're born, you have a certain number of myoblasts that just never develop. Okay, they kind of just hang out toward the outside of muscle fibers. Okay, and they're said to be quiescent. Okay, quiescent. It just means that they're kind of sleeping, if you will, and they get activated through the process of muscle damage. A lot of the things that happen when you lift out, when you work out, but muscle damage and the subsequent repair process. That's kind of what activates them and causes them to start doing something. And the reason you need satellite cells is that um, essentially, if you're going to increase the size of a fiber, you have to add more control um, elements, more nuclei, because as we know from the anatomy of a muscle fiber, each one has many, many nuclei. Okay, it's multinucleated. Um, so as you start adding more myofibrils, you have to add more nuclei in order to control the fibrils that you're adding. Okay, so this is extremely simplistic, but at the same time quite fine for our purposes. All right, so prior to your exercising, you have these quiescent satellite cells. They're hanging out at the outside of the muscle fiber, and they're not really doing anything. You induce some sort of a muscle damage. Okay, you lift weights. We'll just go with that. So you have some sort of, say, mechanical tearing. Some damage happens to the muscle. Okay, that activates and causes proliferation of the satellite cell. Okay, so there's a few places that it can go from there. Okay, one, those satellite cells will activate and they will fuse with an existing cell, and that is hypertrophy. Okay, it adds a nuclei because when that satellite cell fuses with the existing cell, the existing muscle fiber, it just essentially becomes a new nuclei to help maintain that ratio of nuclei to fibers. Okay, now, no, sorry, fibrils. The other option, it can fuse with other new cells and it can cause hyperplasia. Okay, so that new uh, satellite cell would form with other satellite cells and it would create an entirely new cell. Okay, and that new cell would, of course, still be within that muscle, but it's just adjacent to other muscle fibers now, and then it has to be new, it has to be innervated and all that kind of stuff later on. Okay, so the other option is you make more satellite cells. Okay, because at a certain point, if the satellite cells which are just there are being used for either hypertrophy or hyperplasia, then you would run out. So there's a certain percentage that as they become activated, they kind of just multiply. Okay. Now, satellite cells are activated during the latter parts of the DOMS process, delayed onset muscle soreness, and I'm sure you've heard of this before. So muscle damage and soreness are not the product of lactic acid, which is still a commonly held belief, and you maybe have heard of this from somebody down the road. Lactic acid gets blamed for a lot of stuff. It does some things, but it doesn't cause soreness or muscle damage. Alright. The DOMS process is actually an immune system response. And this is kind of what that looks like. Alright. So, a couple ways you can have damage to a muscle. A couple root causes, I guess, if you want to go that way. Alright. So, we have ischemic model. Okay, this is more of a metabolic, so say long distance endurance, something like that. Mechanical trauma, that is more like lifting. Okay, now it doesn't matter which way you have damage, you will have soreness if you're not adapted to that initial stimulus. Okay, so in the case of lifting weights and moving heavy things, that causes damage to the structure of the muscle, typically at the Z disc. Okay, that's where you're actually causing the tearing. Okay, So the Z line. Anyway, you have damage of these structures, and that causes swelling and inflammation. Or if we go to this ischemic model, due to overuse, metabolic acidosis in some cases, you have swelling, increased pressure in tissue, which causes damage, localized ischemia or loss of oxygen, which causes damage, and then that just goes through kind of the same process here. The difference, while you're going to have damage to muscles through both means of work being done, the difference comes in the hormones which are produced, and that's something we'll talk about later in the semester. Okay, that's why you don't see a lot of yoked up, if you will, marathoners. Okay, the kind of damage that you're getting from endurance work is not the same as if you're doing a lot of heavy lifting. Alright, so maximizing muscle growth. Okay, essentially, at all times, you're having a bit of protein synthesis, and you're also having some protein degradation. Okay, people grow muscle, people become larger, they become bigger, from a muscular sense, when they're able to manage the synthesis versus the degradation optimally. Okay, so times when you're degrading muscle, when you're lifting weights, when you're running, when you're doing any kind of workout, to a certain extent you're degrading muscle. Okay, physical activity causes you to damage muscle, and that damage is degradation. Now, that being said, if you don't do those things, then you don't get the response of growth. So, what you want to do, if you're trying to maximize muscle growth, is control that degradation, and as quickly as you can, try to shift over to a more protein synthesis or muscle synthesis environment in the body. Okay, now, you're breaking down muscle often, and we'll talk about this in the bioenergetics and metabolism section. But when your body needs blood glucose, if you worked out really hard and your blood glucose is low, your body will break down protein in order to create glucose to feed the brain. Okay, this process often is called catabolism. Okay, you're essentially cannibalizing your own tissue to feed the brain. All right. It's pretty simple to stop, and it doesn't require you to slug down a bunch of protein shakes. Okay, certainly that will help, but if your body wants sugar, and it's breaking down muscle in order to get sugar, you could just give the body sugar, and then it would stop the breakdown of the muscle actually a lot faster. So, and then it also helps out as well with another thing, which is producing insulin. Okay, so insulin is a very, very, very potent protein synthesis hormone. Okay, you may know it from the fact that having insulin in your system can cause insulin resistance. It can cause uptake of additional fats. It's not really great for if you're trying to lose weight. But if you're trying to gain muscle, insulin is phenomenal, because insulin tells muscle cells to take things up. Okay, it stimulates the uptake of things. Okay, it does stimulate the uptake of glucose, and that's usually why we care about it. But if you're trying to increase the size of a muscle, insulin also stimulates the uptake of protein. And if you're having more protein go into the cell, well, then you're having more ability for that cell to create a structure out of it, i.e. build muscle. Okay, so post-workout, as I've said earlier, you have this kind of window where your metabolism is such that it has increased absorption of nutrients from the blood, and you're also having this increase in protein synthesis. So a smart thing to include in a post-workout beverage, if your goal is to build muscle, is high glycemic index carbohydrates, sugars, the bad carbs, if you will. Okay, The faster it absorbs, the faster it's going to get in your system, and the more insulin it's going to produce. Okay? And that will result in more uptake and more anabolism. So, there's that. And I think I've talked about the rest of that, so let's move on. Okay, so let's touch very quickly on detraining. Okay, we've talked a little bit about training, not nearly as much as it should be, but enough. Let's talk about detraining. Okay, so detraining is what happens when you stop working for a period of time. Okay, so you get injured, you go on vacation, for whatever reason, you get sick maybe, you can't work out. Okay, so let's look at the time course first off, because this happens, people ask me this all the time. So how long does it take before you start losing your muscle? Okay, according to this, control, by the way, here is people who are just continually working. They're not detraining. Okay, so within 4 days, you're seeing a very minimal drop, but 1 week is enough to see a fairly good drop here in muscle mass. Okay, after 14 days or 2 weeks, you see it kind of starts to stagnate. So between 2 weeks and then pushed out, I'm sure this eventually kind of looks like this, but there's a point where you won't go below, and that's kind of genetic person to person. But answer is, within a week you'll see declines. Within 2 weeks you'll kind of stop. You'll have a tapering of reduction. Okay, and the same thing seen here, and this is the cross-sectional area. So that's actually, this is talking about muscle mass, how big the actual muscle is. This is talking about how big the fiber is. Okay, so fibrils within the muscle fiber. Okay, loss of muscle, colloquially we just call it atrophy. Okay, so you're having an atrophy post removal of stimulus. So when you're not exercising, when you're not stimulating your muscles to grow, the stimulus shifts to inactivity / I'm not using it, therefore it's okay if I lose it, if you will. Okay, and that's detraining. If you ever do have a period where you're not going to be able to lift as much, you're not going to be able to move as much, as little as a single set at a comparable intensity to what you're used to doing can pretty much blunt this effect altogether. Okay? So, if you're used to doing a lot of lifting and you're used to, I don't know, being in the gym for hours at a time or something, and you know for a fact it's not going to happen, you can prevent a lot of the loss of your gains, with a Z of course, by just doing a single set. A good one single set on each exercise is sufficient for a little while to keep you from losing too much. Alright, now last little bit here, let's talk about some age related changes that you see with motor units. Okay, so with age we see a general decline in muscle mass. Okay, so you typically see an atrophy occur just due to age. Now it's unclear if that has to do with the fact that people are actually just getting old, or that when they get older they have a tendency to not do as much. And it certainly could be a combination of both. I would wager it is a combination of both. Now, there is something that does occur, okay, and that is the denervation, or the changing, or the reduction in the number of motor neurons interfacing with muscle fibers. Okay, so what you see is kind of a restructuring of the nervous to muscle system. All right, and what you see there is type 2 muscle fibers will lose their nerve. Okay, the nerve that's kind of talking to it. Type 2 muscle fibers, more so than type 1s, will lose that, and a type 1, a type 1 fiber or neuron that's like close, will go and innervate it. Okay, and if I haven't touched on this before, it's something that's worth talking about. Okay, muscle fibers, the type of fiber it is, it also has a neuron that mimics the type of fiber. So if you have a type 2 fiber, a fast twitch fiber, you're also going to have a fast twitch neuron. If you have a type 1 fiber, slower, you're also going to have a slow type neuron. So when these type 2 fibers lose their type 2 neurons, and a type 1 neuron goes and innervates it, when that type 1 neuron innervates that type 2 fiber, it actually shifts the typing of that fiber. So what you see is when people start to age, this graph shows here, you see a decline in overall number of motor units. Okay, if you just look at the clustering here, this is age down here on the x-axis, and this is number of motor units on the y-axis. So people who are between age, say 20 and 40, have a number of motor units somewhere around here, whereas those between 60 and 80 are down here. Okay, so you're having less motor neurons, but also the motor neurons that you have are more likely to be type 1. So you see more slow type fibers coming in and a reduction in type 2 fibers. Okay. Now, as we mentioned early on, the more motor units you have, the more coordinated you are. So, if we're losing the number of motor neurons, if the number of motor neurons is being reduced, you're also going to see a reduction in coordination with age, simply due to that. Alright, and that is it